So I'm going to tell you more of the user perspective of space. A lot of the problems of climate change in terms of land change, flooding, food problems, etc., that we're going to see in the next decades, still require some modelling to understand, some measurements taken to help the models, and so on, because we can't accurately predict many of the major changes that will happen on the planet in the next decade, or even next year probably. So we use a lot of space technologies, and it's interesting that some of those technologies were never intended for this kind of use. It's just like an accidental spin-off. So I'll give you a clue as to some of those things. We're very lucky to be funded by people like Leverhulme, Victorian funders, National Geographic, who are very visionary in terms of funding projects which look at anything to do with the planet. So this is one of the study areas that we're working on in Iceland, because this is the largest ice cap in the region, to see how it is changing. So when we first visited this ice cap, which comes down from a massive volcano, this ice was literally where we're standing, and that's only about 15 years ago. So it's quite a good playground, as it were, to actually investigate how do we measure things, what technologies can we use, how can we do things at low cost in order to monitor the melting and the flow, for example. So one of the things that you can do reasonably easily is use these fantastic synthetic aperture radar systems, which bounce radar off the surface, which means it goes through the cloud, and there's a lot of cloud in these areas, and then you can basically use some maths to calculate velocities. So why are you interested in the velocity of these things? Because, for example, in the Antarctic ice sheets, it's very hard to actually predict how much 0.1 degree of some warm-up somewhere would actually influence the velocity of anything. They're quite complex things, these ice sheets. They're not just a big piece of plastic sat on a rock, sadly. So this kind of thing, where the satellites are going over quite frequently, and the resolution is just good enough that for a big piece of ice, you can actually measure the velocity over like 100 meters squared. And this can feed straight into the models and is used quite widely. And as generations of these things go up, you get higher resolution, you get more coverage, and so on. So it's a great technology for this kind of thing. So part of our work is actually doing ground truth for this, because the uncertainties in this kind of thing, and radar is a low frequency thing for doing these measurements. But we're also looking at visible images from Planet Labs, for example, who have a load of very small CubeSats with cameras, literally flying cameras. And this data gives you, when you can see the surface of the Earth, it gives you nice visual images, multi-band images, so you can do lots of calculations with those, but also you can use them to measure displacement and movement or loss of things. However, our current experience, which Millie's working on, means you have to really hunt for the images that don't have lots of cloud in them, because they're relatively useless. However, they have lots of these satellites, and it's quite easy to have a feed of all those images and actually hunt for the ones that are usable. And use that as like a high resolution, also fill in the gaps. So how are we doing the ground truth thing? For many, many years, people have been using commercial GPS systems. This is where space comes in. Without all the glorious GNSS systems, now called them, you would not be able to have this super high accuracy. So the kind of technology that allows someone to map a street for buildings to the nearest millimeter can be used to record positions of things and then post-process to find out where it is on the planet. But it turns out you need to leave the thing recording all those satellite signals for hours on end, and hours of electronics does not work out with battery packs and weak solar panels in the winter. So we decided to use literally what they use in the street. So you'll see someone set up a base station in a fixed location where they know exactly where it is on the planet, and then they'll walk around with a rover, and those positions are taken to like 1 millimeter accuracy by using the combination of this sending corrections to your rover. So you must actually have a radio link on the surface. So you pick up all these lovely signals at both ends, and then this sends corrections to the other one. It does some more maths, and very quickly, within 1 minute, you can find your location to 1 centimeter. So this suddenly enabled us to not record hours, just have those systems wake up together, link up, wait until they have a good fix, store the fix, and then how do you get that fix back to the researchers in Southampton? We actually put a Meridian modem in there so that it could literally send a very small message, like 50 bytes, to these huge satellites that cover the whole planet very well. There is a slight cost implication of using that space technology, but it works anywhere on the planet, so it means that the system could be designed to work anywhere. So you could put it on the Greenland ice sheet or Antarctica, and you would get the same kind of precision and live data, which is a fantastic thing to get live data back. What else is there to say? Yes, this is low-cost engineering, but the surprising amount of this cycle of testing and bug fixing and re-engineering goes on, because if you leave this equipment out there and then it gets covered in snow, it has huge temperature variations, it's like a tiny little planet of its own. So we have to design it to be very fault tolerant and self-powered. So this is the kind of mess we get into. These Iridium satellite units are used all over the planet because they're fairly cheap to buy. You just, like a phone, you buy a license for it, and you can send messages, almost like text, very slow, very small messages. So it's not like a huge system. Similarly, things like embedded computers, single chip computers, we know exactly what to do with those. It's very easy to choose the right one that has the right power, and so on. Our original early generation of GPS we were using was quite hungry in terms of power, 3 watts or something, but this was a quick prototype put together in about 6 months. So the key for the Earth science people is, do you get useful data? Is it accurate enough? Can they put it where they want, and so on? I won't go through this in massive detail, but this is correlating things like the air temperature to the ice flow. So some of the weird things you can see is that things start to move more when there is just a slight change in air temperature. And of course, once things do move and melt, they create a lake which accelerates the melting, and so on and so on. So it's quite a difficult physics model to explain, also to pronounce. We tend to use just the first few letters of these glacier names in Iceland, just so we remember which ones we're talking about. Yeah, so lots of very useful data came out of it, which didn't require massive amounts of super expensive equipment, which normally means you can only afford a few of these things. When you lose them, it's terrible. With these things, the costs have come down massively because of the drive for autonomous vehicles, cars, handheld devices, and all those lovely GNSS satellites up there. You can buy like a £100-ish GPS, which is centimetre accurate. So it's not the kind of thing you want in your phone, but it is the kind of thing you want on a drone or on a measurement system. So the current generation we're using uses like 100 milliamps, not 3 watts, not massive amounts of power. It's fairly small, very capable sort of thing. So we're doing this, and we're also using a new generation of nanosats by Swarm Space, a Californian company who put up a lot of those ham-sized nanosatellites. All they have on board is communications equipment. So they unfurl their antennas and they just act as a communications relay. So they're much cheaper to deploy in big groups. They've deployed 185 so far They can deploy them in bursts from one flight mission. And for us, the great thing is, not only do they pretty much cover the planet like Iridium, but they want to encourage agriculture and other low data uses of space communications. And so the whole costing of it is more like a cheap phone that you use occasionally, not like highly expensive Iridium system. And these modem things that you buy plug into computers very easily. You can send data up to the nearest nanosatellite that's coming by you, which will eventually send it down to a ground station and get the data back home. So this is kind of an interesting technology for us. We've done a few experiments with these things, and the power usage is actually quite low because it's designed to be a low power, slow, small data type thing. So it's very easy to send small amounts of data very, very cheaply. So people are starting to switch to this quite a lot. Unfortunately, there is a gap in the sky, so you have to do mission planning. So our computer will wake up and say, when should we wake up next when there'll be lots of nice satellites above us? Because if there's no satellite, I'm not staying on because I'll be burning power. So there's all that kind of stuff coming into it as well. So we have like a beta version of the system we're putting into the ICE this summer, which includes like a tiny little 20-pound computer running Python and all things, if you like that kind of stuff. The small satellite system, a kind of a backup, rather naughty backup plan there to use GSM phone system if this can't find satellites, it will pick up the phone. Because they get millions of tourists in Iceland, the phone system is actually run quite nice. Of course, you don't have a phone system in Greenland or the Antarctic ice sheet. So a bunch of electronics. Key things are longevity with no solar power, a bit like going to the dark side of the moon. In the winter, you're covered in snow, there's very little light. You basically need a battery pack that will be calculated to survive. So other things that use the GSM, the GNSS systems, are these drones that they're using to do 3D modeling of the area with imaging, and they similarly rely on the entire GNSS system and real-time kinematic accurate positioning. So these things will know where they are in the sky to within a centimetre or two, and they will tag the photograph so that the photograph knows what it was looking at in terms of location, which is fantastic for the maths you need to actually make lovely terrain models. We're also going to use this without the camera to place small sensor units. So if there are areas which are very far away, across lots of crevasses, not the kind of place where you want to go, we'll fly this to the area and lower some packages with sensors in. So that's a very common thing to do these days. So the kind of models we get from just flying at like 100 meters back up the models that you get from satellite imaging, and you can do differencing on these models to do quite fine-grained, like how much ice has fallen off the front type of calculations. So we look forward to re-imaging all these areas in Iceland. So the space technologies are actually a really good, valuable technology asset for doing earth science. And what people discover is that every time some new innovation comes, very often it's like a satellite system designed for a weather thing or an ice thing, etc., some application. Or sometimes it's a semi-accidental thing where someone's looking at a market that produced a nice system, like Swarm, and we benefit from that because of the costs, size, power, those sorts of things. So yeah, I think I might hit my time. Any questions? Grab your hand, please.
Fascinating. Particularly, I'm really intrigued by the balance of power and weight, and obviously for an academic endeavour, all this cost. But I can see there's lots of market opportunities outside of academia too.